My name's Pete and I like pebbles. I'm a sedimentologist, stratigrapher in the department. I actually came back to Liverpool in about, I think, 2016, and you'll see in a minute why that is significant. So I just want to credit my co-authors here. Emma was an undergraduate in the department. She graduated a little bit under 2 years ago now, and she did quite a bit of the field, well, all of the field work actually for this presentation as part of her ME-Sci project. And James was a postdoc. He'd worked previously on the Triassic as a PhD researcher in Manchester, and then was here for a year working with me on something else, but kind of got involved in this as well, and did a fair bit of the literature review and sort of trawling around for paleo information, such which I might mention. Okay. There we go. So if you walk around Liverpool, particularly South Liverpool, but other places as well, you'll notice there's lots of these red brick walls, red stone walls. And if you look in them, and I tend to look in them as I walk past, right, you'll notice that there are lots of pebbles. And once you get your eye in for those, you'll see them in lots of places. So, for example, in the Anglican Cathedral, there's beautiful cut slabs of this same rock, which is chock-a-block full of pebbles in places, right? So there are pebbles everywhere. There are also some very nice cats. This is just a cat that happened to be commonly walking along the top of that wall when I walked past, and so it got into one of the pictures. Picture's supposed to be the pebbles. And then this spot here, Strawberry Fields, these are the closest pebbles to my house, as it turns out. So they're particularly convenient to take pictures of. But all around Liverpool, you'll see similar things in the rock. So what this made me think when I came back to Liverpool in 2016 is lots of pebbles. Where are they from and how are they significant? And that's kind of a source to sink question, as we would put it in sedimentology and stratigraphy. How are they significant? Where have they come from? So this is what I'm going to try and address in this talk. Here's the outline: an early Triassic single southern sediment source. That's kind of the standard assumption that is used to explain these pebbles. So I'll talk about that a bit. I'll talk about Lower Triassic pebble data that we've collected, that Emma collected predominantly. I'll talk a bit about modeling the pebbles, because that's what we've done for this analysis. The implications of the model best fit specifically, because I think it tells or suggests something useful about that may aid our understanding of where those pebbles are from. And then finally, a bit about next steps, things that we could follow up this research with, and hopefully we'll do so. So an early Triassic single southern sediment source first, right? You can't be a bit of alliteration, can you? So Sherwood Sandstone group strata, outcrop from Devon to the Lake District and further north, right? So the outcrop belt there is marked in yellow, and you can see it runs pretty much all the way up Devon into Somerset, through the Midlands, the east side of the Pennines, west side of the Pennines, either side of the Lake District. And it's essentially post-rift, but heavily influenced by an earlier syn-rift fault structure that's Permian in age. Okay, so there are these faults there that basically seem to bound, or at least partly bound, some areas of the deposition. They certainly seem to be related to thickness variations in the Permian, a bit less so in the Triassic. Significantly, paleocurrent data, and you can see those small arrows on there are showing some of the paleocurrent data that's put together from literature, indicate dominantly northwards transport. Okay, there is some variation, but dominantly northward transport. And the long-standing assumption, okay, or model, or interpretation based on some evidence. One of the reviewers of the paper suggested that we put it that way rather than say it's an assumption, is that the dominant sediment source is in northern France. So that's basically the Armorican Massif, which is this area down here. And it's assumed, or has long been assumed, that that sourced the bulk of this sediment into these north flowing systems. Okay, so we're going to explore that kind of model hypothesis. And here's a representation of that from a quite recent paper, Newell 2018. It's a great paper, actually, really nice synthesis of the Triassic, really good in lots of ways. And it follows this idea that the UK scale regional Triassic paleogeography was largely north flowing, actually from the Permian onwards. Sediment source down here in the south, in the Armorican Massif, and flowing northwards. In the Permian, it was tightly constrained through some graben systems. By the time we get into the early Triassic, Newell argues, and I think this is, you know, it's consistent with lots of seismic data, for example, that it was a broader system. It wasn't constrained so much by the rift systems, but it still followed that north-south trend, and there was some influence from the underlying structure. So, for example, it looks like the Worcester Graben was a conduit for northwards flow that linked between two massifs. So the Welsh Massif and the London-Brabant Massif, which were high areas at that point in the early Triassic. Okay. Now, what's interesting about this is, as a kind of model, in a very simplistic sense, at least, you would think it would suggest that probably decreasing grain size, maybe decreasing heterogeneity as we go north away from that sediment source. Okay, so along the transport system. So this is what we're going to test with some data and with some modeling. Is that really the case? Is that what we actually observe in these Triassic rocks? So a quick look at, because we're in Liverpool and this is our local geology, I thought it'd be nice to just go through very quickly some of the units. So the Sherwood Sandstone group divided into 3 formations. Got the Chester Formation, the Wilmslow Sandstone Formation, and the Helsby Sandstone Formation. And the lithostratigraphic subdivision, as lithostratigraphy tends to be, is a bit complex because there's heterogeneity, right? So these units are a mix of fluvial and aeolian strata, and they do show significant lateral variation. And that makes it a little tricky sometimes to figure out what you're actually seeing when you're standing at a particular exposed outcrop. Because, you know, which is it? Is it an aeolian-y bit of the Helsby, or is it a more fluvial-y bit of the Wilmslow, for example? So there's this complexity that we have to try and tackle. And I mean, the British Geological Survey have done a pretty good job, actually, on their maps, I think, of sorting this out. So let's just go through those units. The Chester Sandstone Formation, and these are a few exposures of that around Liverpool. The Hale Lighthouse area there is some really nice exposure of these units. You can see they're basically cross-bedded, reasonably coarse-grained, locally conglomeratic, I'll come back to that in a second, red sandstones. They're fluvially dominated, or the Chester Sandstone Formation is fluvially dominated, but there are some aeolian units, okay? And I've worked on aeolian units in the past, and it's actually sometimes a little tricky, in my opinion, to really see where how much of that influence is present, because diagnostic features are a tad tricky. And exposed in quite a few places around Liverpool also. So the Woolton Quarry is another place where it's very well exposed in South Liverpool. And there you can see also that it's faulted on a variety of scales. You can also see, if you look carefully in here, pebbles, right? So there's quite a few pebbles scattered through the sandstone. Okay, the faulting, that particular faulting is younger. It's, I think, probably Upper Jurassic in age, beautifully exposed in other parts of the UK, like down in Somerset and in the Bristol Channel. But I think those faults, they're perhaps reactivated Permian faults, early Triassic faults, but I think the most recent activity on them is probably Upper Jurassic, late Jurassic. And then the Wilmslow Sandstone Formation, this is formerly the upper mottled sandstone, because it is quite mottled. There's actually an exposure of it just up there from where we are, mostly hidden under a bush. But if you look carefully and you walk around campus looking for exposures of this, you'll spot this one. And it's actually right by a fault which runs through campus as well, which is interesting, but I won't go into that. But there's an exposure of that just up the street. Mostly, though, it's not so well exposed in the Liverpool area. A place where it is exposed, and you can go and look at it, is in the Pure Gym car park in Brunswick, down on the dock road. And I've crept into the car park and stood down taking lots of pictures and tried not to get spotted and arrested by the gym security staff. But it's beautiful, well sorted, medium grained, large scale cross bedded. it looks there to be pretty much Aeolian dominated, okay? But it's hard to find good exposures of it around Liverpool. And then finally, the Helsby Sandstone Formation, coarse-grained, locally conglomeratic, cross-bedded red sandstone again, so, you know, pretty similar. Also mixed fluvial Aeolian, but here, in this unit, I think that interplay of Aeolian and fluvial stuff is particularly complicated, right? Because you can see in different places, it's quite a profoundly different dominant or less dominant influence of those two systems. So if you go along the street from here, that way, and you're brave or foolish enough to hoist yourself up the wall a little bit and look over into the Edge Hill cutting beneath, that's what's pretty much beneath our feet. Beautiful, big Aeolian dune cross sets, truncated. They look as though they've got grain flow units coming down the front of them. Absolutely fantastic. I'd love to actually be able to walk through there without being hit by a train. It'd be really nice. But you can at least look at it. I shouldn't advise anybody to do that, right? The reason my hand is in the picture is because you have to hang on quite tight whilst taking a picture with one hand and hanging onto the wall with the other. But the same Helsby sandstone, it's exposed on the Wirral. The Thurston Road cutting is the basal part of it. And there it's pretty, you know, it's quite a big Aeolian influence, same as around here. But over at Alderley Edge, lots of pebble beds there. So that's a place where it's got more fluvial input. So it's pretty heterogeneous. This is the youngest bit of the Sherwood Sandstone group, right? So if we were expecting a decrease in heterogeneity going upwards through the Triassic, that doesn't seem to be what's happening. I'll come back to that in a minute. Okay, so as well as the variability that I've just shown you around Liverpool, that same variability is pretty much reflected across the whole of the southern UK. So we've got apparently correlative lithostratigraphic units that have been defined. You can see they change from place to place. So I think now this is kind of, so the British Geological Survey does use Helsby Sandstone, Chester Sandstone Formation. They use that across the country for their maps, right? Other people use, though, different local names, but these local names are, you know, they're pretty well established. But what this is reflecting is a degree of heterogeneity as you go from south in the Wessex Basin, north to the East Midlands, and then further up into the Cheshire Basin. Okay, and the Wilmslow Sandstone Formation is basically, it's present in some places, other places it's not. So in some places you can subdivide into 3 units, in other places it seems to be only 2. There's a significant unconformity in there. So actually, there's quite a lot going on. Okay. And this is the point. It's a bit more complex, perhaps, than one might expect for a tectonically quiescent, simple south to north transport system, right? So this is one of the things that makes it interesting to explore a bit more. But now let's come back to this key question. Pebbles are common in the Chester Formation. They're abundant locally in the Helsby Sandstone Formation. So does that distribution of the Chester Sandstone Formation pebbles particularly, are these pebbles really all from the same source on that Armorican Massif in northern France? Is that really where they've all come from? This is what we're going to explore. And that's the same thing on map form, but it shows 2 places that are kind of an alternative hypothesis of where this sediment might have come from. The Welsh Massif, the London-Brabant Massif. It seems likely to me, and it always has, that those are feeding sediment into the system as well as coming from that southern source. So how can we actually test how much that might be the case? And it also raises this other question: could that heterogeneity persist in Upper Triassic strata? And I'll come back to that at the end. So let's look at the pebble data. So Emma went to several outcrop locations to collect data for her ME side project. She also compiled data from a few literature sources, places where she didn't go, down in the Worcester Basin and Wessex Basin, a bit too far for a day trip. And she basically measured pebble concentration. I'll explain that in a minute. And she did the same thing, applied the same method to actually exposed outcrop photos from published literature, right? So there's these 2 sources, either her own field work in all these examples at the bottom of the table, or from published literature at the top. And in each case, she knew the distance from the Armorican Massif, and she measured a mean pebble concentration. So let me just explain how that was done. She basically counted the pebbles, measured their size. She did this for 9 to 18 randomly positioned measurement boxes like this per exposed outcrop site. I think it's probably about 10 or so spots per area where she worked. And she counted the number of pebbles and the size of pebbles in each frame. And that allowed us to calculate the pebbles as a kind of concentration. How much of the total sediment area or volume is represented by pebble? That gives us this concentration. And we can then replicate that same process using the published literature. Right, so this is, I went here last week actually to just have a look myself. The Chester Canal units are just showing how a few of these 15 by 15 centimeter boxes placed over the exposure. And there's one that Emma did herself in the Hawksmoor Wood formation down in the Midlands. Okay, so these are the data that she collected. The red circles show pebble concentration in the different locations. Size of circle indicates concentration. You can see the size of the circle in Chester and this Farndon Cliff in the Cheshire Basin, quite a bit lower concentrations there, higher concentrations here, high-ish concentrations there. So that's basically how it breaks down. And we've looked at the distribution of the concentrations in each case. So we've got an idea of how they're distributed, and that helps us understand what's going on in each case. Not always normally distributed, but I think probably that's a slight sample size issue. Okay, but as far as we can see, there's no problems calculating means from those, and looking at the Budley, Salterton and Foxenholz data, which we've measured from literature, again, it looks to be broadly similar in the nature of the distribution and such like. So we're not seeing any reason for concern in what's been measured. But now let's get to the best way to plot that data. What we can do for each of those locations is we can calculate an approximate distance from the Armorican Massif, a point chosen in that area of northern France. We can plot the pebble concentration against that distance, and this is what we see. The Wessex Basin concentration is reasonably high. It declines by the time we get into the East Midlands and the Cheshire Basin, but then there's this also high part here, which is basically Worcester, Needwood, Hinckley, Staffordshire Basin, so in the Midlands. Okay, so what we can see straight away, that is not a simple smooth decrease from south to north. If you were expecting the pebbles to decrease in abundance and concentration going north away from that source in the south, doesn't seem to be that that's what happens looking at these data. And you only need to go to some of those outcrop locations and see the concentration of pebbles there to realize that straight away. But plotting it makes it particularly apparent. Okay, so what we're going to do now is run some models to try and explain how what that distribution of pebbles with distance from the potential source area might indicate. So let's model those pebbles. And I've done that with the simplest possible representation of pebble concentration or sediment concentration away from that point that I could think of. Okay, so what this equation basically says is we've got a proportion of sediment that's deposited per unit distance, and you basically say, okay, what's the volume at the previous distance, and then to calculate, what's the volume at the previous distance? That's V of a particular volume of a particular lithology at X minus your unit distance. You use that multiplied by the deposition proportion to calculate a new volume at the distance that you're looking at, position of X, right? So this is like, I think in maths, it's called the recurrence relationship. Pretty much the simplest way you can model any kind of sediment transport. And I'll show you what it does or how it plots in a second. It's a very simple model. Importantly, it's quick to compute. You can download it, load it from GitHub, which is not an auspicious name for a software development site, but it's there. And because it's quick to compute, we can calculate many, many thousands of iterations very quickly. And we can use that quickness to compute then to make convenient best fits against this data. So this is what I'm going to show you next. So let's just start with some simple model output. So this is that same distance profile, so 0 to 700 kilometers. This is the same distance profile that I plotted the data along in a minute ago. And what we've got here is total sediment volume decreasing away from the source as deposition occurs, and then sand and pebble volume. Okay, and basically that's what the transport that's what that transport relationship gives you. Okay, so it assumes that sand tends to be transported further before deposition than pebbles, and that's because there are two decay constants for the rate at which the sediment is deposited, and the decay constant for the sand is slightly lower than the decay constant for the pebbles, so the sand goes further, basically. Okay, and the model can have one source, as in this case, or we can introduce multiple sediment sources. So what I mean by that is, along the profile here from south to north, we've got an input point at x equals 0, but we've got another input point at x equals 300. And the point of this is it allows us to consider what the distribution of pebbles lithology would look like if we had more than one sediment input point. And that's what we're interested to explore, because the hypothesis is, could some of these pebbles have come from local sources, not just that source in northern France. Okay, and that's total volume, and this is the same model output but showing proportions. So now we're talking about proportion of sand at distance x versus proportion of pebbles. You can see the proportion of pebbles drops off because the sand goes further, proportion of sand remains high. So it allows us to actually make a comparison with what we see in outcrop. That's kind of the point of doing it this way. And with a really, really simple model, of course, it's easy to say, oh, it's too simple. Well, it might be, okay? But in my experience, starting with the simplest possible model first is usually the best approach. If it turns out that you can't fit the data, or that it can't explain certain aspects of the data, which I think ultimately will be the case with this, then go on to the more complex models, introduce more processes, make it more realistic. But if you start with the simplest model first, it's quicker, it's easier, you're not making more assumptions than you need to make. Okay, so that's the reasoning behind it. And then finally, in the sort of explanation of the method, we need to be able to calculate an error. So now those blue dots are the observed pebble concentrations along this transport profile from, so this is the Wessex Basin, Budleigh Salterton pebble beds there. These are the Cheshire Basin, Chester Canal location there. And you can see in each case, we've got a concentration of pebbles that's predicted by the model, and we can calculate how that differs from those outcrop points at each position along the x-axis. Right? And from that, we can generate an error. And the units and such of the error don't really matter. So basically, we need an error so that we can calculate the relative merit of different models to calculate which fits best. The error is basically calculated then as the sum of those line lengths, basically, the deviation from those points from that model line. Okay? And there's a few more details in there, which I don't need to explain at this point to make the point that we're trying to make. Now, once you've got the model, once you've got a way to calculate an error, you can do some what we call Monte Carlo method best fit analysis. So all this means is you generate lots and lots of models. You select parameters using a random number generator. You run the model, you see what error you get, you repeat. It's the simplest possible way that you can find a best fit. So it's just sheer, bulk, what's the word? Brute strength computation to try and find when you get the lowest error. So what the animation is showing you is iterations of this model, of this method, and the error in each case. And what you can see is the error drops. What's happening there is you're remembering the lowest error model that you've found so far, and you're recording that as your best fit. And you'll see the error drops progressively, and you can see visually the fit tends to improve as we go through these 200,000 iterations. That takes a few minutes on a reasonably powerful desktop computer, so it's pretty fast. There are much more sophisticated ways of doing it, but this kind of does the job to at least get started. Okay. All right. So what do those best fit models tell us? Well, let's just do a bit of playing around first. If we consider a single southern sediment source, kind of the best fit error we can get with that is this 1.41, right? If we ignore those data points there because they're inconvenient, we can make the fit much better. We can say it's 0.03. Clearly, we can't ignore data points, but this is just to illustrate the point that The Chester Basin stuff kind of seems to show what you could model as a southern source trend, but these points in the Midlands, they mess that up. You can't get a good fit with those pebble concentrations observed in outcrop at that distance. Okay, so what we need some other way to explain it. We need probably different sediment source models to generate a best fit. And here's essentially the best fit models that I've seen this method generate. So this is basically assuming that we've got that one trunk river system, but with multiple tributary river sediment input points. This plot has got one tributary input point. This has got two. This has got three. And you can see the input points are where the total pebble proportion spikes. And this one with two tributary systems gives us basically the lowest error that I've seen this method generate, more or less. If you run it for 2 million times, you get like a fraction of a percent lower error or something, but I don't want to run it for that long typically. But this gives the lowest error, and you can see it's got an input point here, it's got an input point here, and you can see the purple line basically goes through most of those blue dots, indicating that it can explain the data that we observe. Now, this is not saying that's the only explanation. It's not saying this is what happened. It's simply saying that a multiple source model is a better explanation of what we observed than a single source in the south model. That's all it's saying. So let's not overinterpret here, but it does suggest that these early Triassic sand and pebbles were from northern France for sure, that southern source, plus probably two or more proximal UK sources that fed tributary rivers and explain why the pebble concentration is more complex. So what's the implications of that on a map? So now our map is looking subtly different. If you look carefully, you can now see these blue lines that I've drawn in very cartoon manner coming off these, the London-Brabant Massif, the Welsh Massif. What we're suggesting, what the best fit suggests is that there are input points where these red kind of wedges are located, input systems into this north-south transport system, right? This can explain why we see the pebble concentrations that we do. This is important because it's saying, look, it's not just that what we observe, it explains the observed heterogeneity, but it also strongly suggests hints that there's going to be more heterogeneity than we would perhaps expect if it was a simple south to north system in the units that we can't so easily go out and count pebbles in outcrop, right? So it's a prediction of heterogeneity. This is probably important for all sorts of things now. So, you know, reservoir quality issues, basically for water, CO2, nuclear waste storage, not so much in the Sherwood Sandstone, but in the younger stuff. I'll come to that again in a second. Okay, so this is the main conclusion. This is now, we're just about to publish this. It's just got to finish the revisions and resubmit it next week. So it should be published quite soon. So the next steps then, this needs more data, first of all. I mean, it's a bit, we haven't included any Liverpool data here, which is a bit mad. So that's probably the first thing to do in this northern part, fill in the data gap there. But there's also a very significant data gap between the Wessex Basin and the Worcester Graben, where we just don't, there's no outcrop, there's no exposed outcrop, right? So that's in this area here. And it would be very interesting to see how that pebble concentration that we observe down here decays or changes northwards before we see it high again here. If it does decay rapidly and then rise again, that would be strong evidence that the model is, you know, suggesting something reasonable. If it remains high all the way through, that might be, well, more interesting to try and explain, right? So that data gap is a critical one to try and address, I'd say. And also, pebbles are not the only thing you can do. Lots of other people have done heavy mineral analysis, but it's interesting. They don't tend to interpret it so much in this kind of more regional manner. They just tend to say, in our basin, there was a bit of sediment coming from the east, there was a bit coming from the west. They don't tend to put it together into this more holistic picture. So maybe a literature review to do that would also be useful. And then this question about the persistence of heterogeneity through into the late Triassic. That this paper Newell 2018 has this lovely plot, which shows, it seems to suggest greater climate variability from carbon isotope data in the early Triassic, decreasing and becoming more stable, perhaps in the middle Triassic to late Triassic. I don't know, I always struggle to interpret out isotope curves a bit like this, because there seem to me to be quite a lot of uncertainty associated with them. But you know, if we take that to be true, does this mean that lower Triassic heterogeneity is likely to be greater than upper Triassic heterogeneity? If it's forced by climate, perhaps that's what you would conclude from this. But if there are lots of proximal sediment sources that can maintain significant heterogeneity being fed into these upper Triassic units, perhaps not. Perhaps the heterogeneity will be maintained, right? So there's a really interesting question here about tectonic control, climate control, or something else that's to do with the denudation of the hinterlands that are feeding this sediment transport system. And all of this has definitely got important implications for, you know, all the things that I just mentioned, heterogeneity of sealing units, basically. So finally, one way to explore this further is to use some numerical forward modeling. And there are several models that do this now. They couple a landscape evolution model with a depositional model. So you can basically model what's being eroded, and you can model where it's transported, where it gets dumped, right? So Badlands was the first one that did this, but there's this new one called Go SPL. And this is some output from Badlands. And you can see it basically produces that there's your upland source area. It's like a sheet of sediment that is then itself denuded further by these lovely, beautifully modeled river channel networks. Okay, so this is a DEM of the UK, which will be a starting point to define an early Triassic and a late Triassic paleogeography. If I were doing this project, I would start by editing that to represent the paleogeography as we think it was early Triassic, late Triassic, run this model on it, see whether anything like this comes out of it. Okay, and then one final thing. There are lots of methods now to actually combine multiple models together and to produce map type output. And this is particularly useful for this type of problem where you're trying to understand spatial heterogeneity. So this method that's shown here, you basically take lots of model scenarios, you combine them in a way to actually calculate the probability of some output from the model happening in a particular spot. So this map here is green is indicating places where there's lots of thick sand, red and white are indicating places where the model realizations, 100-odd models, are showing that it happens very rarely. Okay, so you can perhaps see then how we could use this method, a model like Badlands or Go SPL, combined with that paleogeography to produce maps like this across the southern UK, saying, you know, for the upper Triassic, you're likely to get a lot of sediment input from a proximal source here, here, and here, right? You could start to predict those locations where this might happen. Okay, so conclusions. Quantitative modeling is always useful, I think. Others may disagree, but I think it is, especially when constrained against data. The point of it is usually to test and challenge existing interpretations. That's when it's most useful, right? You can test whether things are consistent, they make sense. In this case, the best fit models generated from this method suggest multiple sediment input sources, not just one in the south, but multiple along that transport system, probably then suggesting greater heterogeneity than would be expected from that simple model. Lots of questions pop on from that about evolution of the sediment transport system into the late Triassic, when it's probably increasingly important that we understand how it worked. Okay, thank you for your attention.
The obvious one is what about the petrology and the pebbles themselves? Do they differ from different potential sources?
So yes, you can basically identify some of the sources that they've come from. So and I think most of the work on that has been done in on those Devon and Somerset ones there. Some of them definitely do seem to have come from the Armorican Massif, in the sense that you can link them back to units that are outcropping there now. But they also come from the Canubian batholith area, okay? And in the middle, but then the other thing people do, not just petrology, they look at the fossil content in those pebbles, right? And that's a very interesting story. And I didn't put it in because it just takes a bit too long to explain. But essentially, the ones down in Devon show fossil content that is at least partly from the Armorican Massif. People had assumed that the same was true of the fossils that are present in pebbles from the Midlands. But when we've checked this more carefully against more, but a lot of that was published like 1940s. It's not been worked on for a long time. So we've checked it against a recent paleobiology database. And it turns out that actually the stuff in the Midlands, there's a collection of pebbles and associated fossils in the University of Birmingham. It turns out that that is not a Gondwanan affinity fossil fauna as that would come from the Armorican Massif. It's Laurentian, so it's come from somewhere further north, and there's actually a band of outcrop that you can see in that database where the fossils have been found that could have sourced those pebbles. So it's kind of it's kind of saying, it's kind of supporting what the modeling is showing, that there's more than one source. Okay, but you could do a lot more of that, and I think probably more has already been done to show that there are lots of these local sources, but people just haven't really brought it together into a synthesis. Yeah. So I think there is some of that goes on. So people argue, for example, that in the Hellsby, those are recycled pebbles from the Chester Formation below. And I mean, they may well be.
What about the old going back in, let's say, going back into the older sandstone, where there are plenty of conglomerates which themselves have been recycled.
Indeed. So they could well be, yeah. But I mean, it doesn't really matter to the analysis actually in that sense. They've come, they've come from somewhere. The question is whether they're recycled in that way or whether they're weathered from original, bedrock. I'm not sure that makes too much difference to the transport system.
I mean, I can see many issues with all. I'm not saying there's anything wrong with the models. So, the model is a good test, starting point to test hypotheses. All sorts of technical struggles here.
Yeah.
Just out of interest, Andrew Morton's published a recent paper on Carboniferous.
Right.
Fluvial dispersal systems or fluvial dispersal, whereas identifying multiple sources across the central Pennine Basin. So that is an example of the type of thing that potentially you would try to do.
Yeah.
This is huge.
On the scale well, I think that's the issue, isn't it? That's the issue. It's a really big job. And I know there's a PhD student in Imperial who's working on this currently. I don't know how much of that provenance analysis he's going to do. No, I don't know. But you're right, Steve. The model is just a way to sort of lead you into the question and then help you actually figure out what kind of data you need to collect next. That's the way that I see it, to highlight the fact that it's a bit more complicated than just that southern source. Because even in that Newell paper in 2018, he's still kind of saying it's coming from the south. Oh, but there's a bit of detail that there's bits, he doesn't really explore the issue properly, in my opinion. Richard.
Sorry, question. I was just going to say I agree very strongly with this. And I get the idea that there are all sorts of complexities. You can actually get point is to take a simpler model and see how much of the biopics you can express. Now, as soon as you start getting into the multiple sources, you end up down a rabbit hole where there are, let's say, more hypotheses and data you can get at, but you do the simplest thing you can. About what you presented, I could have dealt with. How do you done my data modeling course?
There you go. There you go. I'm usually only doing the modeling. It's a bit of a departure for me to deal with the data as well. Yes.
Why is that not spinning?
Oh, it's just to make it more interesting, right? So that you can see the delights of the Lake District from multiple angles.
You should think up.
I remember about 20 years ago, you asking the same question to someone else in the audience who gets another. That's sort of amusing. But when it comes to the data, when you collect the information, you're using little
Yes.
But I mean, this is a long time geological problem.
Yeah.
So have you considered sort of doing, is it proportions of the data you collect, or is it a proportion of the rock? Or no, that
Well,
would provide.
Yeah, it's a sample, isn't it? And this is one reason why I went last week to look at the outcrop, to try and get a sense of how that sampling might work. I mean, I think if you take 10 to 20 samples per site with that method, you get probably something that's a reasonable estimate of that pebble concentration.
You probably have to say.
You could take a lot more.
Let's say more, 130. Just to really categorize an outcrop.
Maybe. Well, it depends, doesn't it? It depends how heterogeneous it is. It depends what the concentration's like, really. But you know, what you could test that easily by simply subsampling and seeing how the distribution and the mean changes as you increase the sample size to what you've got. I've not done that, I must admit, but you know, maybe we should.
Yeah, because I mean, it's sort of a thing that's happened. Similar as that people get directed to the pebbles, and so they go on the entire system. Go, oh, there's no finding in the system.
Yeah.
Pebbles, the proportion of sand. No.
Yeah.
So they're just measuring the pebbles, and it doesn't find.
But there is,
just measuring pebbles.
but there is finding. We can see that in the pebble distribution.
Yeah.
It's just that the finding is not following that simple north-south pattern. It's a bit more complicated, right? And I mean, you know, the other thing that does freak me out slightly is there's probably a lot of variation in the sedimentological processes that produce those individual beds that have got the pebbles in them, right? We've not really looked at that at all. I mean, to collect more data on this, that is one of the things that you would need to do. But the purpose of this is really just to flag the point that there's something more complex going on than simply everything coming off the Armorican Massif.
Well, again, I think it's great, Roger. So I'm just interested. So the error bars on that data would be interesting on those blue bars.
Yeah. Well, yeah, it depends what you mean error. They would be the variance bars, wouldn't they?
Yeah.
And that's what the distributions are showing.
Okay,
so you could plot them on that plot as well, couldn't you?
Yeah. So you have each one of those plots on there as a data point, and
it's mean. It's average.
So you do have error bars on there.
Yeah.
And are those error bars fed into the best fit model?
No, it's simpler than that. And they could be, but I'm not sure it wouldn't be so straightforward to generate what a best fit then, would it? You could do, I mean, we could do that easily. Yeah.
For the basin inference, if you want to go there, but frankly, I would my team for that.
It's kind of works.
Thanks for doing this. I feel that I appreciate what I'm saying, but sometimes an obsession of error and
yeah.
Well, not being one thing, and there's actual ways. Yeah, the problem is there are so many error bands that aren't.
Yeah.
It's hard to read your observation around.
Right, but what you've got to remember, Rob, is that before this, all we had was a cartoon, and that's typically all that comes out of field data. Outcrop analysis is a cartoon, right? So you know the imperative is to do more than that, right? That's always my point. If all you've got time for is the cartoon, that's fine, right? And you know you're happy with something like that without the added blue bits. It's cool. But you can add more quickly just by doing some of this. And there's all the caveats with it, of course, but you still know more after you've done that than you did before, even with this, even with all the uncertainties that you're highlighting. Right? The uncertainties were there before, it's just you've highlighted them through doing a model, I would say. Yeah.
But you model in exactly the same way, things like sphericity or pebble size distribution.
Yes, I think so.
Yeah.
If you can find what you would consider to be a physically reasonable way to actually generate that mathematical model of that property, then you could do it. Yes, following exactly the same method and with all the caveats that Rob and Steve have highlighted. Right, you must not overinterpret what you get from it. But yes, I think you could. I mean, and the question, I think, the thing that's interesting is, do you though have to go, well, when you go to something more sophisticated like this, where does that then lead you? Because of course there's a whole, this would look superficially like it was more sophisticated and complex, but actually all you've really done is built in a load of assumptions that really just make it more uncertain. So I would be inclined to do this kind of modeling as a follow-on to what we've already done. But you're not necessarily that the simple approach applied to some of the forms of the data might actually probably be also a sensible thing to do first. I think, yeah, you're right.
Sorry, so Dave led that question online, and he mentions that since the Sherwood is considered a potential geothermal resource in the UK, with potential new predictions and heterogeneity using techniques like this, help delineate more promising targets from the reservoir quality point of view.
I don't know how much that impacts the flow of water through a rock like this. I mean, less than it would impact the flow of hydrocarbons, for example, where they're more viscous and so the porosity permeability is more important. Maybe less than it would be important for CO2. But in principle, yes. I mean, I guess it's certainly quite a bit harder to drill a pebbly sandstone than it is to drill a nice, soft, clean sandstone. So drilling costs, which are probably critical for geothermal projects, that would definitely be influenced, wouldn't it?
Anyone have any other questions for Pete? No.
What's your favourite pebble?
Actually, I can't answer that question. Seems wrong to have a favourite pebble. I do have favourite pebbles, but not from the Sherwood. I've got lovely pebbles, got little very thin turbidites in them from North Wales, and one that's got a lovely little fault in it. But quartzite pebbles, honestly, really, I shouldn't say this, but they don't float my boat quite so much. Cross-bedded pebbles.
What's the little arrow pointer in there?
Oh, yes, I forgot to mention that. Sorry, that was for John Wheeler, who I've talked a bit about with this, and who where is it now? He has there we go. Yeah, he has John is unimpressed by pebbles, so I was trying to hook him in and say, but John, it might be an eclogite, because I mean, the pebble beds there have come off an eroding orogenic thrust belt, right? So I mean, I don't know, maybe it's been clear. It was a Wheeler hook. It didn't work because he's not. Yeah, it's not the most convincing of arrow labels, is it? Yeah, I should have mentioned that because it's a bit random. True. Cool. Look, thank you very much for your time. I enjoyed doing that. Thank you.